This is a potential difference question and it applies to AS1 from 2000 and it's question 6. So the first few bits about Kirchhoff's first law. 6.1 shows a junction point 0 in this part of an electrical circuit. There's 3 amps going in here and there's 5 amps going in there. And so this is the junction here at O. Conventional currents of 5 amps and 3 amps exist in the branches OX and YO as shown. According to Kirchhoff's first law, there must also be a current in the branch ZO. Kirchhoff's first law states that charge is conserved at a junction point. Explain how this applies at junction O. So at junction O, the total charge entering must equal the total charge leaving the circuit. And therefore, since Q charge is proportional to I, the same applies, same is true for I. I should really write junction here actually. Okay. Right, next part of the question. Deduce the magnitude of the rate of flow of charge in the branch ZO. So rate of flow of charge is just I, because it's Q over T. So we're looking for I. And therefore, if you have a wee look back at the circuit, you can see there's 3 amps going in, but 5 amps going out. So there must also be 2 amps going in that direction from Z. And so we'll just write down 2 down here. And the direction of the current flow in ZO, so it was from Z to O, and so it's the second box. Last part of the question, find the number of electrons per second passing through a cross-section of OX, and therefore there's OX there. And so we want to use our total number of electrons and our total charge. So we'll use the equation Q is equal to NE. So Q is equal to NE, and Q is also equal to IT, where T is 1 second. And the current in that part of the section was 5 amps. And so if I just rearrange this, N is equal to I over E, and I is 5, and E is 1.6 by 10 to the minus 19 electrons. And the answer just comes out then as 3.13 by 10 to the 19. It's always a huge number for the number of electrons or electron flow rate, and that's per second because we have put in a second there into the diagram, even though I didn't put the T in. Right, the next part of the question then shows a potential divider circuit. So figure 6.2 shows a potential divider circuit which can be used to provide various potential differences to an electronic circuit. Find the potential difference between the points W and X. Now, if you have a wee look at this, you can see that you could work out the potential differences across each part and then check that the potential difference here, what's it compared to the 6 volts here if we attach a lead across. So that's done quite simply. The ratios there are, if I write them, well, the ratios from P to Q, Q to R, S to T, and R to S, S to T are 2 to 6 to 3 to 5, and that is spread across, that's 12 volts that's spread across that. And so you're finding 2/16, that's 2/16, 6/16, 3/16, and 5/16. Now, it's going to be connected across here if there is anything connected, and therefore we've got a total, if I just put a wee line down through that, of 2 and 6/16, 2 and 2/6, and in total that's 8/16, which is half. And since that resistance there is half of the total resistance, and this voltage is half of the total voltage, therefore the potential difference between here and here is just going to be 0, because you have 6 volts in total across here, and so the potential difference is just 0. Points W and X are now connected by a wire of resistance 100 ohms. What is the current in the wire? So again, what we can do, we can have a wee think about just what happens here. So the current is flowing. Say we do connect a wire, and I'll just put it in here. The current's going to go down that way and round, okay? There's going to be an equal amount of current coming out here as there is here. And that current's going to come over here, round, through the same amount of resistance and up that way there. And those two currents are going to cancel each other out completely because they're exactly equal, because you have a voltage and an equal amount of resistance here as you have here and here, and therefore the answer to the second part is 0. A wee bit of a giveaway is the fact that that is only worth 1 mark, so it's just really something that you're kind of understanding from the diagram rather than having to calculate. Now the third part of the question, the wire between W and X is then removed. Complete table 6.1 giving the potential differences between pairs of output terminals of the potential divider arrangement. For each pair, state the relative polarity of the terminals. Indicate the relative polarity by placing a plus and a minus sign in the appropriate boxes. So what we're trying to find is the potential difference between R and S, R and Q, R and S, and S and Q. So the first one there, if we look back again at the diagram, we're ignoring this line again. And so it's first one's between R and S. We'll just work them all out. The total resistance in the circuit is just those all added, which is 1600 ohms. So the current in the circuit is V over R, which is 12 over 1600 ohms. And that gives you a total answer of 7.5 milliamps, or 7.5 by 10 to the minus 3 amps. Therefore, across each one, all you need to do is multiply each one by 7.5. And so if I'm just going to write them over here, the first one here is going to be 200 times 7.5 milliamps, which is 1.5 volts. The second one is 4.5, and you can check this out between the calculation yourself. 300 times 7.5 milliamps is 2.25, and 500 times 7.5 milliamps is 3.75 volts. Right, so the first question then in our table over the page asks you to fill in the potential difference between R and Q. Between R and Q we have 4.5 volts. And it says put in the relative polarity of R to S. So if we have we look there, R is on this side and it's closest to the negative, and Q is on this side and it's closest to positive. So Q is positive and R is negative. The next one then is R and S. So go back to the diagram again. Between R and S there we have got 2.25 volts. R is closest to the positive side, S is closest to the negative side. So R is positive and S is negative. Put that in first. And it's got a total potential difference of 2.25 volts across it. Okay, S and Q then, so we'll go back here again. So between S and Q is here. So we've got the addition of the two resistors in here. So that's 4.5 plus 2.25. And that gives you a total of 6.75. S is going to be negative and Q is going to be positive. So minus and plus, and the total addition was 6.75.